A very good afternoon and welcome to all the course participants and course coordinators. I am Ashutosh Bhardwaj, faculty from Photogrammetry and Remote Sensing Department, Remote Sensing and Geoinformatics Group IIRS. Today we are going to start the module 2 on Global Navigation Satellite System. It will be consisting of 8 sessions and one demonstration on GPS. So today we will be covering the introduction part, introduction to GPS and GNSS. Then tomorrow we will cover the GPS receivers, processing methods, errors and accuracy. Then after that we will cover the satellite based augmentation systems, signal characteristics followed by demonstration, and then we will touch upon the mobile mapping, Indian regional navigation satellite system and GPS aided and geo augmented navigation, that is Indian Gagan system, and a special lecture on the GNSS radio occultation. Besides this, we have put the course material at the location. You can download that, and this time I have given a ebook also, which is freely available on the internet, and you can download it also. I have given a PDF also for this. This is the GPS, the first global navigation satellite system by the Trimble. So this is there as a PDF in your material, as well as it can be downloaded. So we will begin our first session today. So today we will cover about the introduction to GPS and GNSS. GPS is the global positioning system and GNSS is the short form of global navigation satellite system. So basically GPS is a surveying equipment and it serves our requirement to prepare maps, and then we have added applications on that. The basic problem is same as our historical problem, that is of the origin and the destination. Previously, the first maps were mental maps. Early hunters and gatherers used mental maps to navigate overland. Then historically we have seen that various civilizations, they have developed their own methods to prepare maps which have been very accurate. Then in the surveying, we see that various instrumentations has developed over time, such as chain, tape, theodolite, compass, dumpy level, tilt levels, total station, electronic distance measurement, EDMs, and then GPS has come. The previous instruments before GPS, all of which has been using the triangulation and trilateration to solve the surveying problems, has one common requirement, and that requirement was clear line of sight. So whenever it is happening that you have to survey between 2 points A and B, they should be clearly visible if you want to do the survey for both the points in a single step. If there is any hurdle in that, then you have to go round about the hurdle, and then you cannot do the measurement in a single step. But with the GPS coming into picture, GPS do not have the line of sight requirement. So this condition which have been there with all the instruments which developed earlier, that condition is waived off now with the development of the GPS. So as historically I was telling, humankind, they have been using the celestial navigation. That means in the daytime they have been using sun as a means of locating the direction, and in the night time moons and stars, they have been used for the purpose of navigation. This kind of celestial navigation was good enough for latitude, but it was poor for longitude, because the longitude calculation requires time. So until 1760, when a good clock was invented, the calculation for longitude has been a challenging task. Then over the time, various instrumentations has developed, like magnetic compass, gyro compass, radio direction finding, radar and inertial navigation system, Lauren A, and then Lauren C later on, and in between Omega and the transit, which is also a satellite based system, it also developed. And in 1980s and 90s, then the GPS has come. So in all these instrumentation, Only the transit and the GPS, they are satellite based systems, and all other systems are ground based systems which has the condition for the clear line of sight. Now, how well does these individual systems work? So we'll see that the Omega system, the initial system, it was having an accuracy of about 2 kilometer, which has improved over time to 1 kilometer, and then 400 meter, and then in the transit, which is a satellite based system, to about 200 meters accuracy. Lawrence, which is a ground-based system for particularly the commercial ships moving in the Atlantic and Pacific oceans, is also providing an accuracy of the order of 180 meter. GPS is giving us an accuracy of the order of 15 meter. So about 10 to 20 meter accuracy we are receiving from the GPS depending on the time when we are surveying and what kind of constellation is above us at that point of time. Now let us see the early space-based radio navigation system. See, first thing, what has happened during the time of the launch of Sputnik? So Sputnik was the satellite which was launched in 1957 by Russia, that we have been tracking the Sputnik based on the Doppler shift. The altitude of Sputnik was 985 km above Earth and the revolution period was 98 minutes. At this point of time, when the Sputnik was launched, there was a person known as Frank McClure at the Applied Physics Laboratory who made a suggestion that would it be possible to invert this problem. So he made a suggestion. Now we have to understand his suggestion. See, he has talked about inversion of the problem. So first we have to understand the problem so that we can actually invert the problem. So the problem which existed at the time of Sputnik was that we know our position on the ground, that is on the earth, but we want to locate the position of the satellite in the space. So once we launch a satellite, it is visible to us till some distance and then it moves out of our eyesight. So we do not know where the satellite is there and we need to track it. So ground position is known, but the space where the Sputnik is there or the satellite is there, that particular position is not known. So inversion of the problem means, is it possible that we know the positions in the space in the form of satellites and we can track the position on the ground? So that was the idea which was given by the Frank McClure, and it has been developed over time and resulted in the formation of the transit in the late 1950s. So United States of America, they started a space-based program in which they launched 6 satellites. Now the position of the satellites in the orbit is very well known. These satellites were an altitude of 1100 km with a revolution period of 108 minutes, and based on the position of these 6 satellites, the position of receiver, the receiver which receives the transit signals on the ground, can be located. Now we are calling it a transit and not a GPS because transit was a system which has a specified coverage on the earth. It do not cover the entire earth. This was primarily to meet the requirements of the Cold War at that time between the US and Russia. When the transit was developed, parallelly another system known as Cyclone, it was developed by the Russia. This system consisted of 10 satellites, and the Russian system has been divided into 2 systems called Paras and Cicada. So Paras was a military system which was again having 6 satellites at an altitude of 1000 km, whereas Cicada was used for commercial and civilian applications. It consisted of 4 satellites. So basically the Paras system and Cicada both together form the Cyclone system. So one was the Russian system, another was the US system. These two has developed during that time. Now these systems has been primarily used for helping the navies in that time. So it is also known as the Navy Navigational Satellite System or the transit. It was used for observing the Doppler shift so that it can calculate the distance and position of the satellites with respect to the receivers so that the position of the receiver can be calculated. It was working till 31st of December 1996. I will tell you how and why it was working up to 1996. There was a limitation with this system that it only gives 2D location, that is we can calculate the latitude and longitude, and it takes about 40 minutes of time. Once you switch on the system, it requires 40 minutes to get you the position. In today's GPS system, you switch on the system and we will get position into hardly 2 to 3 seconds. But whereas it was taking about 40 minutes earlier. Another difference with the today's GPS is today we are getting latitude, longitude and height, all the three, whereas the transit system was giving only 2D. But let us see here what was the aim of the transit at that point of time. It was trying to help the commercial or the navy ships at that point of time. So we know the position of the ship vertically already, that it is on the surface of ocean, which is roughly near to the mean sea level at some point of time. So the requirement was also 2D in that time, and the third dimension was can be considered as known. So this system was working perfectly for that particular application. Now we have seen like Lauren A and Lauren C, they were the ground based system like our mobile tower systems what we are using today for getting mobile signals. So similarly, Lauren A and Lauren C has been ground based systems which are basically high frequency short wavelength radio signals. But with these signals, there was a problem that they get attenuated when they travel through the various kind of mediums and they interfere with the vegetation and the buildings. So these systems, ground based tower based systems were having problem as compared to the space based systems. Another problem with the ground based system is that they are limited to the objects above the ground. Whereas the advantage with the space based system is that they can look at a larger part of the earth at any point of time. Now, when the idea of the global positioning system was made, at that time the United States of America, the Department of Defense, that is the DoD, they have prepared a definition for it and they decided to establish, develop, test, acquire and deploy a space-borne global positioning system, and this system has resulted into the formation of Navistar GPS. So the full name of GPS, what we are used to call as, is actually Navistar GPS. The full form is Navigation, Satellite, Timing and Ranging Global Positioning System. Now what is the formal definition of it? The formal definition is that it is an all-weather space-based navigation system developed by US DoD to satisfy the requirements for the military forces to accurately determine their position, velocity and time in a common reference system anywhere on or near the earth on a continuous basis. So this is basically the boundary condition with which the system has been prepared. We know that the GPS is giving us the latitude, longitude and height, which actually mean the position. But in this definition, we can appreciate that it is actually serving three purposes. It is not only giving us the position, but it is giving us the velocity also of the receiver, and it also gives us the time. And actually, as the GPS uses atomic clocks, it not only gives us the time, but it helps us in maintaining the definition of the time. And all this is happening in the common reference system. See, all the countries across the globe, for the purpose of mapping their own land, like in India, we have defined a best fit for the Indian region, which is called the Everest ellipsoid. So Everest ellipsoid is the best fit for the Indian region, but not for the global, that is not for the entire earth. Whereas the global positioning system is working on WGS84 datum, which is a ellipsoid which is the best fit for the entire earth. So based on that WGS84 datum, all the calculations of global positioning system are being done. The general characteristics of GPS are that it is owned by United States of America Department of Defense. It is an accurate navigation device giving accuracy of the order of 10 to 20 meter. It has a worldwide coverage. It is 24-hour accessible. It works on common reference frame, that is common coordinate system. It is designed to replace existing navigation system. It is accessible currently to both the civilian and defense establishments. As I have told you earlier, it was primarily meant for the defense, as it was basically a development of Cold War. But once the Cold War has opened, it has closed. Now the applications have come in the civilian domain, and daily new applications are being coming up for the GPS. The first GPS satellite, which was named as PRN-4, PRN is the acronym of pseudo-random number, which is a kind of nomenclature being used in the numbering of the GPS satellites. So PRN-4 is the first satellite of the GPS series, which was launched on 22nd February 1978. Like we have first generation computer, second generation computer, similarly in case of GPS, we call them blocks. A block means a satellite, a GPS satellite, which is of similar in nature, using similar kind of technologies. What has happened over the time that the electronics has improved and the mass of the payload has decreased and the efficiency of the payload has increased. So based on the technological changes and various other technical things which build the system, the GPS satellites are being placed into different blocks. So the block 1 consisted of total 11 satellites, first being launched on 22nd February 1978, and these launches has been from 1978 to 1985. All the satellites of block 1, what we can call as the generation 1 GPS satellites, have completed their life. The block 2 actually has many multiple series within the block 2 because of the incorporation of different technologies within that. So block 2 and 2A satellites, they were launched between 1989 to 1997. First launch has been on 14th April 1989. Then block 2R and 2RM, these has been launched with new frequencies like L2C and code M on both L1 and L2 frequencies. We will see gradually what are these L1 and L2 frequencies. Overall, in the block 2, total number of satellites launched were 27. One was for block 2, 14 satellites in block 2A, 12 satellites in block 2R, and 8 satellites in block 2RM. So like this block 2 has been there. Additionally, block 2 has a series which is currently running, that is block 2F. Block 2F is the series which is currently running. The last launch of block 2F has been on 15th of July, in which was the 10th launch of block 2F satellite, and currently this series is running, and now we are looking forward for block 3 satellites to be launched too soon. Launch date of block 3 was scheduled at 2014. It is delayed, and let us hope that it will be coming up soon, which has more powerful frequencies and has anti-jamming features with the strong signals. Like we have mobile jammers, so GPS also we have GPS jammers. So block 3 satellites will be little bit strong enough to not to get into the jamming. So it will be available even if the jammers are being there. Once these systems have been launched in 1993, the initial operational capability has been declared, that the system is declared that it is functional. and it has been under testing and evaluation over time, and the full operational capability of GPS has been declared on 1995. So like this, 1995 full operational capability of GPS has been declared, and then you can understand in the previous slide as it was written that transit system has been working till 1996, December 1996, so that there is some kind of overlap between the two satellite based technologies. So once the full GPS is operational, transit is no more required. So transit has been stopped functioning from December 1996, and we have switched to GPS. If you have to understand GPS, we can divide it into three components. One is the satellite based component, which includes the satellites in the orbit. And then once the satellites are being launched, somebody has to take care of the health of the satellite. We have to monitor. So there are ground segment. So we call it a control segment, wherein we have the master control station and the monitoring stations. And then we have the users who actually use the GPS service. So we have three segments: space segment, user segment, and the control segment. The primary space contractor has built the system. That contractor name is Rockwell International. Then it is shifted to Boeing, and then currently Lockheed Martin is making the GPS systems. The coordinates reference which is being used here is WGS84, as I have already told, which is actually the best fit ellipsoid for entire Earth. There has been a huge cost of about $12 billion. It is only the initial cost, and yearly maintenance cost is about $400 million. So it was $12 billion which has been put into the system initially, and then this is the recurring cost every year for maintenance of the system. It is being operated by US Air Force Space Command, the Mission Control Center operations from the Schriever, formerly known as Falcon, AFB, at Colorado Springs. So like this, these three segments are there. Now the space segment, the first one of the GPS space components, has been built like this so that there are 4 satellites in 6 orbital planes. So these are the 6 orbital planes. As you can see, these black lines moving at an 55-degree over the equator. So this is the equatorial plane, to which there are orbital planes, 6 orbital planes. So the entire equator is 360 degree, as we know, 360 divided by 6. So 6 orbital planes are there 60 degree longitude apart. So at every 60 degree we get one GPS orbit. In each GPS orbit we have minimum 4 satellites. That makes the count 6 into 4, 24. So 24 satellites are there to function all around the globe, so that they gives us the position over the earth. The system is being managed by US National Space-Based Positioning, Navigation and Timing Executive Committee. These orbits are 12-hourly orbits. At any station on the ground, they are visible for about 4 to 5 hours. The initial design life of the satellite was 7.5 years. The new satellites which are now coming up, they have even higher designed life, more than 10 years. The orbit is about 20,200 km above the Earth, and every satellite is placed so that minimum it is visible from 2 ground stations. So these are the locations of the ground stations as a part of control segment. So previous slide we have seen the space segment. Now we are talking about the control segment. So Colorado Springs is the headquarter, that is the master control station. It has a monitoring station, and then we have monitoring station at Hawaiian Islands, Ascension Islands, Diego Garcia and Quezon. And ground antennas are also there. Besides this, we have many other surveillance stations also placed around the globe, but this formation was the initial formation. Master control station has the responsibility to collect all the tracking data from the monitoring stations and calculating satellite orbits and clock parameters. So that is the job of the master control stations. All the corrections are being carried out by the master control station. Whereas the 5 monitoring stations, which are actually the real ones to keep in touch with the satellites, they are responsible for the routine maintenance of the satellites. They are responsible for measuring pseudo range data, that is the distance between the satellite and the receiver. It is called pseudo range because there are certain errors in the range. Range is nothing but the distance. So because of the error, the term pseudo is being used in front of range. This orbital tracking network is used to determine the broadcast ephemeris and the satellite clock modeling parameters. So when the satellites are being in touch with all these 5 stations, because one of the station cannot keep in touch with all the 24 satellites or the number of satellites which are there in the system, because usually the number of satellites which are there in the orbits is about 30 or more than 30 nowadays, because it has become a very important system and under no condition we want it to fail. So there is a lot of redundancy currently in the GPS satellites, and we have higher number of GPS satellites as per the requirement, because initial mathematical requirement was of only 21 satellites, but the configuration made it 6 into 4 24 satellites, and in reality we are actually keeping about 30 plus satellites nowadays in the orbit. These ground control stations have the antenna also, which can upload the information to the satellite vehicles. These are S-band antennas and they are used for the uplinking. So any updation has to be done on the satellite. So ground station is being used. User segment. Nowadays, everyone is user. Knowingly, unknowingly, many of us are using GPS. Our mobiles are GPS enabled. The cars, the taxis in which we are traveling, they are GPS enabled. The facilities we are using, like the trucks, buses, trains, aircrafts, all of them are having GPS installed on them. So there is a big user segment of GPS now. Now, why we are using GPS? We are using GPS because it is weather independent. Rain, fog, snow have no effect on signals. It does not require clear line of sight, as I have initially told. Like in case of other traditional surveying equipments, we require clear line of sight. That condition is not required here in case of GPS. It has high geodetic accuracy. That means it takes care of the curvature of the earth also while deriving the coordinates. It can be operated day and night. It requires less manpower. It is very quick. It is highly economical. It works on a common coordinate system, that is the WGS84 datum, and it has a wide range of applications, and it is very competitively priced. Once we need to purchase the system, and then we need not to pay any charges for GPS. Now let us see how it is working actually. So as Frank McClure say, the problem has been actually inverted. The GPS satellites, which are actually moving in the orbits at 4 km per second, are actually acting as the reference stations. A boundary condition has been used in the system that these are all one-way ranging system only. That means GPS satellites only send signal to the receiver. Receiver do not send any signal to the satellites, because it was a development of the Cold War, and the condition has been put that the signals should only be received by the receiver. Receiver should not send any signals for the security reasons. The signal which is being received is time tagged. So when the signal starts from the GPS satellite, the time is there within the signal. The transmission, each signal consists of the transmission and ephemeris data also, that is the coordinates of the satellites in the orbit. That is how they are acting as the reference stations. So signal is time tagged. So let us say T1 is the time at which the signal starts from the GPS, and T2 is the time at which the signal is reaching the receiver. So that is T2 is the time of arrival, and it is compared with time of transmission. So T2 minus T1 is the total time, that is delta T, which the signal has taken to come from the satellite to the receiver. This delta T When we multiply it with velocity of light, it gives us the range, that is the distance between the satellite and the receiver. Each range puts the user on a sphere above the satellite. I will explain this diagrammatically again. And when we intersect many such spheres, it will give us the user position. So diagrammatically, let us see here. The signal is beginning from the satellite at time t1, reaching the user at time t2, and t2 minus t1 gives the delta t, that is the time of travel multiplied by velocity of light, gives us this distance. When four such satellite signals are received by the GPS, we get the position with an accuracy of 10 to 20 meter in general, and previously we used to get 10 to 100 meter because of a phenomena known as selective availability, which I will explain tomorrow. So the range is equal to time taken, that is the delta t, into the speed of light. How the spheres are being made, let us understand here. So the position of satellite, which is acting as a reference station, is very well known, as you can see at the right top. With the pseudo range, we can create a sphere, and so this is the condition. One sphere we have created. When we get signal from two satellites, we get two spheres which intersect each other. So that means now we are somewhere in this region. When we intersect two spheres, it results into a circle. And when the third satellite, that is the third sphere, also intersects, it results finally into 2 points. So we know that on these 2 points the receiver is there. Out of these 2 points, one point is the real point on the earth, as you can see on this colored diagram, and the other point is a vague solution which is actually outside the earth. So that is how three satellites can give us the position. Although there is a reason why we need fourth also, that we will discuss further. So how is it working? The satellites are actually behaving like an orbital control station. They are giving us the distances to prepare the spheres to intersect each other, and then give us the finally the coordinates. Now what is happening in the GPS receivers? We are using cheaper clocks, that is the quartz clock, not like the satellites wherein we are using the atomic clocks. So there is a precision difference between the two type of clocks, which gives us the fourth unknown parameter, which is called clock bias, which becomes the fourth unknown. And because of that, we require, instead of 3 satellites, 4 satellites to solve the equations. This time is a very important factor to be seen here, because time is being multiplied by velocity of light. A minor error in time results into huge error in the distances. So let us see how it is working. If we are wrong by 1 by 10 of second because of the clock bias that we are using in the receiver and the satellite. Satellite is using atomic clocks, whereas the receiver is using quartz clock. So 1 by 10 second of an error can result into an error of 30,000 kilometer, whereas the diameter of the earth is about 12,600 kilometer or so. So that means 30,000 kilometer, that means we are away from the earth. Now if we are having a microsecond error in the timing, then also we are out by about 300 meter. If we have an error of nanosecond, then also we have an error of about 0.3 meter, that is 30 centimeter, which may also not be tolerable by certain applications. So that means we need clocks with an accuracy of more than nanosecond. So basically we are using clocks which are actually accurate to the order of 1 in 10 to the power 13 or even better. So now what we have understood is that we have 4 unknowns now. One is the latitude, second is the longitude, third is the height, and then fourth unknown is the clock bias, which has come into picture because of the two different type of clocks which we are using on the receiver and the satellite. So 4 unknowns, so we require 4 independent equations, and that is why we require now 4 satellite vehicles to be in touch with the receiver. Under the ideal conditions, if similar clock would have been used on the two satellites and the receiver, three satellites would have been sufficient. But since the clocks are different in the satellite and the receiver, the situation is like this, that we require four satellites. So because we have four unknowns x, y, z and b. If Doppler is also tracked, velocities can be computed. So now with each satellite we are making a equation. It is like simply 2D equations. If we know the x1 y1 and x2 y2 coordinates between 2 points in 2 dimension, the distance is root of x1 minus x2 whole square plus y1 minus y2 whole square, that we know. Similarly, in 3 dimension, the equation is p1, that is the pseudo range, that is the distance between the satellite and the receiver, first satellite and the receiver. So x, y and z, these are the coordinates of the receiver, whereas x1, y1, z1 are the coordinates of the satellite 1, which are known. x2, y2, z2 are the coordinates of the satellite 2, x3, y3, z3 are the coordinates of the third GPS satellite, x4, y4, z4 are the coordinates of the fourth satellite. So in this equation, only x, y, z is unknown along with the b, which has come into picture because of the difference between the atomic clocks and the quartz clocks. So four unknowns are there: x, y, z and b. Pseudo ranges are known, and x, the satellite coordinates are also known. So xi, yi, zi are the positions of the ith satellite vehicles. Here I would like to tell, the naming of the GPS satellites or the GNSS satellites are being done so that they are either represented as SV numbers, that is satellite vehicle numbers, SV1, SV2, SV3. So they are called by SV numbers or by the pseudo random numbers, that is PRN1, PRN2, like that. So these are the two ways each satellite has been numbered. Along with the signal which we are receiving a 50 Hz signal which is modulated on L1 and L2 carrier waves, which actually have the navigation data and the timing information. This also we will see in detail. So GPS time is little different from the universal coordinated time. GPS time is considered to be started on 6 January 1980 at 0 hours. It was the first Sunday of 1980. The UTC timing, which is as per the Zulu calendar, and it is considered as the civilian time across the globe. It starts from January 1, 1972, but the GPS time is referred from 6th January 1980, and there is a difference of around 13 leap second on 6th January. Because it is a variable term, this difference changes with time. So GPS time is actually international atomic time plus 13 leap seconds on 6th of January 1980. Satellite vehicle clocks are now accurate to 1 part in 10 to the power 13. As I told you, this term is variable, but it is taken care by the GPS authorities, and the number is being fed by them into the systems so that the user do not need to worry about the timing. Effectively, GPS time starts with 0 at the beginning of each week. So that means the timing in the GPS is little different as per our regular dealing with the timing. Now we will see the GPS signal structure. How is it? So basically, GPS signal are the signal which they carry is the course acquisition code, that is the CA code, and the precise code, that is the P code. P code is used for the defense purpose by United States, and it is encrypted code, that is why it is known as Y code after encryption. This code we cannot get. It is only for the US and allied nations under NATO. So there will be specific receivers which can receive the P code. So our work is mainly being done by the course acquisition code, which has a frequency of 1.023 megahertz. The frequency of P code is considered the fundamental frequency. When we divide the fundamental frequency, that is 10.23 megahertz, by 10, we get the CA code frequency. When we multiply by 154, we get the L1 carrier wave frequency and multiply by 120 we get the L2 uh, carrier wave frequency. So basically the CA code and P code are to be sent from the satellite to the receiver, and they need some carrier to carry them from the satellite to the receiver. So there are two type of carrier waves. One is the L1 carrier wave, another is the L2 carrier wave. Now we can note here the coarse acquisition code, which is of 1.023 megahertz, which has a wavelength of about 29 meters, is actually modulated only on the L1 signal. Whereas the military code, that is the P code, that is the precise code, because there is another M code which is also known as military code. So we need to segregate the M code and the P code nowadays. But in the initial GPS, P code only used to be there, M code was not there, but nowadays M code is also there. So P code is on both the wavelengths, carrier waves. Besides this, we get a 50 bit per second satellite message also, which consists of almanac and ephemeris data. Almanac is Almanac gives us the position of all the satellites, GPS satellites in their respective orbits, whereas ephemeris gives us the momentary or the instantaneous position of the satellite in an orbit. Besides this, there is a frequency called L3 at 1381 megahertz. It is used for nuclear detection. So any nuclear detection is nuclear detonation is happening anywhere on the globe. US detects it using the L3, but it is not for us. And now from the launch of Block 2F satellites, we are having L5 frequency also recently added up, and it will be helpful for us in the indoor applications in the coming days. Besides this, we have to understand that the P code is having about 290 meter wavelength. L1 wavelength, that is L1 is the carrier frequency, is about having 19 centimeter wavelength, and L2 is having about 23 centimeter wavelength. So L1 is the shortest, L2 is the next bigger than that in terms of wavelength, followed by coarse acquisition code at about 29 meters, and then coarse acquisition code is about 290 meters and precise code is about 29.3 meters. Also the bandwidth of L1 is 24 megahertz, bandwidth of L2 is 22 megahertz, and bandwidth of L5 wavelength used, which is the carrier wavelength, is also having 28 megahertz wavelength. So this particular slide is very important, which actually explains the structure of the GPS signal. So I will repeat here, the acquisition code which we are using is the coarse acquisition code. Coarse acquisition code is overlaid only on the L1 wave, whereas the precise code which is used by Department of Defense, it is being modulated on both L1 and L2 carrier waves. So now the precise code, as I was telling, has wavelength of 29.3 meter. It is about 10 times faster than coarse acquisition code. It is actually a very long code. It is 2.35 into 10 to the power 14 bits code, which is a period of 266 days. The calculation of P code vis-a-vis the other codes I have explained in the previous slide also. When the P code frequency is divided by 10, we get the coarse acquisition code frequency. When we multiply P code frequency with 154, we get L1 frequency, and when we multiply P code frequency by 120, we get the L2 frequency. So main thing to understand here is that P code is a very long code, as it is for the defense. Nobody should be able to crack it, and it is having a period of 266 days. Now let us see the coarse acquisition. On the contrary, the coarse acquisition code is very small, only 1023 bit long. It has a wavelength of 290 meter, and it has a period of only 1 millisecond. The service given by CA code is known as standard positioning service, whereas the service given by P code is known as precise positioning service, that is the PPS. So SPS is the service given by codes acquisition. Initially, the intention was that CA code will be used simply as an acquisition code for P code, but later on CA code has been used for the civilian applications. Almanac, as I was telling, Almanac is giving us the position of the satellites, GPS satellites in their orbits. It is like the nakshatra chart of our astrology, which actually gives the position of different stars in their orbits. Similarly, Almanac also gives us the position of satellites in their orbits, but here the concern is about the artificial satellites, which are the GPS satellites put by us into the orbits. When GPS is used the first, it has no idea about the location of the satellite, so it is known as cold start. But once it locates the GPS, then next time we need not to update it. It is always able to take it the position of the GPS satellites as per the almanac. Until unless it gives some problem. If some problem is being given, then again we have to feed the satellite positions once again. Once we switch on the GPS and it starts its operation, it nearly takes 12.5 minutes to get the entire almanac downloaded. Next comes the range determination, that is the distance calculation between the satellite and the receiver, that also based on the code observation, that is the CA code or the P code in case of the defense systems. PRN, that is the pseudo random number, it uniquely identifies each satellite. As I was telling, PRN is a nomenclature like the satellite vehicle, so it identifies each satellite. It gives timing coordination for each of the GPS. PRN also gives the pseudo random number, the code which comes. It also gives the information about the timing, and it enables amplification of the signals also when the signals are weak. Each satellite sends a unique signal which repeats itself approximately every 1 millisecond. A similar signal is being actually given by the receiver also. Here lies the technique by which the problem of clock bias is being resolved. Same signal is being given by the satellite, which is actually the part of the complete signal. A similar signal is being given by the code. Now they should actually perfectly match, but because of the clock bias, they do not match. So because of that, we run a correlation process in which we find out how much is the difference by which we need to shift the receiver code with respect to the satellite code so that they can be in the sync. So this delta t represent the shift which is actually happening in the signals because of the synchronization problem, because of the precision differences between the satellite atomic clocks and the quartz clock. So if we are able to get hold on this delta t, then we can resolve the clock bias component. And that is how we actually calculate the clock bias. Now, and then using the code and the timing signal, we can calculate the distance between the receiver and the satellite with the corrections for the pseudo range because of the clock bias. So like this, we calculate the distance between the satellite and the receiver using the codes. Now similar exercise can be done based on the phase of the GPS signals instead of the code. Now this is being carried out because this can be done very accurately to an accuracy of the order of an error of plus minus 1 degree of the wavelength or the phase. That means if we are using L1, which is 19 centimeter wavelength, 1% means 0.19 centimeter, that is 1.9 mm. So if we do the phase order observation, we can have an accuracy of the order of 1.9 millimeter if we are using L1 wavelength, and 2.4 millimeter if we are using L2 wavelength. So this was actually not part of the initial planning. The initial planning was only about the code solutions. When we started using the phase observations at a later date, then we started getting phase solution, and that has come out to be better than the code solution, because code solutions has been giving us accuracy of the order of meters, whereas if we apply certain procedures which we will discuss tomorrow, we can get accuracy of the order of millimeter and centimeters by using the phase solution. These also use self-generated signals, as I was telling in case of the code solution, to compare the receiver and the satellite signal, and solve the clock bias problem. The equation here is being used to see d distance, that is the pseudo range between the satellite and the receiver, as c into delta t plus lambda times n. So n is the number of wavelengths which are there between the satellite to the receiver. When the signal starts from the satellite, it completes certain number of integer number of wavelengths before striking the receiver. Now it is not necessary that when it strikes the receiver, last wavelength is full. That may be a partial wavelength. So that partial wavelength is represented in terms of phase, calculated in terms of c delta t. But the integer number of wavelength is represented as lambda n, and this number n is actually known as the ambiguity. So this complete number of wavelengths which are being completed by the signal while reaching the satellite is known as ambiguity. So this distance from here to the satellite is lambda n, whereas the partial wavelength is this phase measurement. If we combine the two, we can get the exact distance between the satellite and the receiver. Once we start getting the distance signal from the receiver, then as the time moves and the satellite moves, we always know how many complete cycles has been completed, but still the ambiguity remains. So this ambiguity is actually equal to this distance only. So this is basically the unknown which we need to calculate in order to find the pseudo range, and this is the part of the processing which we will see tomorrow. Now there are four methods to do the GPS surveying. One is the static method, another is the rapid static method, then stop and go method, and then the kinematic method. So these are the four methods used to survey. See, nowadays we all are using satellite imageries, and we understand that once we get the satellite imagery, we need to georeference it. So for that purpose, we need the control points which we acquire through one of these kind of surveys. How these surveys are different from each other will be covered tomorrow as part of the processing of the GPS signals. So for today, I will tell that these are the four procedures we are using: either static, rapid static, stop and go, and kinematic. So the details I will be giving tomorrow about these four kind of surveys. Then when we are using the GPS, we need to know how the signals are reaching, what is the quality of the signal. So like we use in statistics the term root mean square error, in case of GPS we use the term dilution of precision, which is a unitless number, and it gives an idea about the quality of the signal, and it is user friendly because it is like a thumb rule given in terms of the unitless number, so that general user can also understand it. In GPS we are using trilateration only because we are dealing with distances only, no angles are being used. Those who are doing surveying, they know we can make triangle by using one distance and two angles, or we can make triangles by knowing the all the three sides. So basically we are using the trilateration technique, that is the second one. So when the user is interested in knowing the accuracy with which the signals are coming to us, what is the quality of them in terms of latitude, longitude, height and time, it is known as geometrical dilution of precision. Whereas if the user is not interested in time, he is interested only in latitude, longitude and height, it is known as positional dilution of precision. If the user is only interested in latitude and longitude, it is known as horizontal dilution of precision. If user is only interested in vertical height, then it is known as vertical dilution of precision. So DOP value, if it lies between 1 to 3, it is considered very good. If it lies between 4 to 5, it is considered good. If it is about 6, it is considered fairly good. If it is more than 6, it is considered suspicious. So we do not use the values if we are getting dilution of precision value more than 6. If we have a widespread GPS constellation above the user, then it is considered good. But if it is a skewed set of, that is on only on the one side, it is considered poor. It is so because when the ideal satellite geometry, wherein one is considered to be above the head or the above the receiver, that is the GNSS position, and three equally spaced in the coverage area, what happens? The uncertainty is minimum. Whereas if similar or more number of satellites are there, but they are skewed, that is more towards one side, what happens while making the spheres, which we have discussed earlier, they intersect into larger portion and the uncertainty is high. So it is preferable that if we can receive signals from spread set of satellites, we get better accuracy. Like the sunrise, satellites also rise and decay, that is, they fall. So when the satellites are rising, what is happening? They are traveling longer distances and they have more errors. So we prefer to not to use the satellites when they rise up to certain degree, and also we avoid the last signals which are received by the satellite. So when the satellite rises from one direction and moves and falls in another direction, so that is horizon to horizon, we do not use the part of the signals from each side. This angle as shown here 15 degree, for which we do not accept the signals. See, this 15 degree is not a fixed number. We can change it. It can be 5 degree, 10 degree, 15 degree, any number we can choose, because higher the number, less will be the number of the satellites in the coverage area. So this is a trade-off actually, how to fix this number. So this number, that is the angle, is known as mask angle. So this fixing the mask angle is actually a trade-off, because if we increase the mask angle, then number of satellites decrease. If we decrease the mask angle, then we start receiving signal from the far end, which has more errors which need to be corrected later on. Now we have single frequency receivers which can give us accuracy of the order of 1 centimeter to 5 millimeter plus 2 to 1 ppm, because the earlier receivers which were coming, they were giving accuracy of the order of 1 centimeter plus 2 ppm, but the latest receivers which are coming, they are giving accuracy of the order of 5 millimeter plus 1 ppm. Single frequency receivers means they only receive L1 signals, so L2 is not accessible to these. The limitation with this one is that for this we can survey areas which are within study area limits of about 15 kilometers. If we have larger study areas, then it will be difficult to use single frequency receivers. They will give less accuracy. Whereas in the dual frequency receivers, we get even more accuracy, 5 to 3 mm and 1 ppm plus 1 ppm. So latest receivers are giving about 3 mm plus 1 ppm accuracy. These are used for geodetic control networks, tectonic plate monitoring, network densification, national network creation, photogrammetric control, and very detailed surveys where high precise accuracies are required. Theoretically, they do not have limitation like 15 kilometer, which we have in case of single frequency receiver. So actually the procedure like differential GPS, which we will talk tomorrow, we operate two GPS together. One is at a known location, another is at an unknown location. This we will discuss in detail tomorrow. So in this case, the distance between the two receivers is known as baseline. So longer the baseline, longer is the time of operation, which we call static operations. If these are shorter, then we take observation for less time. That is known as rapid static survey. So these are the dual frequency receivers which receive both L1 and L2 signal. Then there is a error budget. Every component which is being used to calculate the distance between the satellite and the user accrue some kind of error within the total calculation. That is the calculation of the pseudo range, that is distance from the satellite to the receiver. So there is a error in the satellite clocks which actually incorporate error of an order of about 1.5 meter in the pseudo range. See, this is the error which is in the calculation of pseudo range. That is the distance calculation between the satellite and the receiver. Then there are errors because of the orbital errors. It can contribute up to the order of 2.5 meter in the pseudo range. Ionospheric errors, when the signals travel from the ionosphere, it also gives a delay, which again we will discuss tomorrow in detail. It also gives error of the order of 5 meter or more. Troposphere also contribute to an error of about 50 centimeter or more. Receiver noise, like every electronic instrument has its own disturbance basically, which we call as a noise. It is also giving an error of the order of 30 centimeter. Multipath error is giving around 60 centimeter error. Then selective availability is giving about 30 meter error. So initially when this phenomena known as selective availability was known, the accuracy achieved was of the order of 90 or 100 meters in 3 dimension. Now this selective availability has been switched off. What is this selective availability? We will again be discussing tomorrow. This was an intentional degradation done by US Department of Defense so that users do not get good accuracy. It was operational till 1st May 2000. So it was giving a large amount of error into the calculations, but nowadays it is no longer there. So instead of about 90 to 100 meter error, we are getting accuracy of 10 to 20 meter. So our accuracies which we are actually achieving nowadays is much better. The user range errors consist of the system errors, which consist of the ephemeris data and the satellite clocks here, whereas atmospheric errors are because of the ionosphere and the troposphere. Equipments error are the receiver noise and the multipath error. The positional dilution of precision, if it is coming to, it can be considered as equivalent to that if we have a 1 meter of user range error, then it will result into 2 meter of the positional error. It is an analogy, not an exact conversion. So it can be understood like that, because PDOP, as I told you, it is a dimensionless number. Then we can have differential GPS accuracies. This we will detail tomorrow. Now once the systems have been prepared by various countries, as we can see on this slide, Navistar GPS is by United States of America, GLONASS is by Russia, Galileo is under construction by European Union, then BEDO is by is by China, BEDO, QZSS is by Japan. So now in the earlier days, for each of these systems we need to have a different receiver, but now in 2006 the Russia and the US, they agreed to share the codes which actually enabled the formulation of single receivers which can receive both GPS and GLONASS data. This has given the birth to the new term called GNSS, that is Global Navigation Satellite System. So, GNSS is a system which uses basically more than one constellation of satellites. One constellation belongs to Navistar GPS, that is of the US. GLONASS belongs to the Russia. When we use both together, it is called Global Navigation Satellite System. Not only that, with time there are systems which has evolved on the ground in the aircraft also. So the GNSS has become as a super term in the GPS domain, which has a very broader acceptance for different systems working towards the same goal, giving us higher and higher precise positional values. So let us see the theoretical definition of the GNSS. So GNS is a worldwide position and time determination system that includes one or more satellite constellations, aircraft receivers, system integrity monitoring, augmented as necessary to support the required navigation performance for intended operation. So it is a very complex system, including all the technologies in air, on satellite, and on the ground. So it is a multi-modal system which has bases on air, sea, land, everywhere. Combined together, it is known as GNSS. We will further discuss GNSS tomorrow. Now, as per the various users, we can see that this particular table gives us an idea of accuracy which is required for particular domain. So each user can fix in their own domains and look at themselves. Like in geodetic infrastructure fault monitoring, we need better accuracies in terms of centimeters. For resource mapping, we can have 20 centimeter to 1.5 meter accuracy also. For GIS data collection, for utility mapping like power GIS and other things, 1 to 5 meter accuracy is also fine. For reconnaissance survey, 10 to 100 meter. So each of the user can place himself or herself in this particular table and can find out what kind of accuracy is required for their work. So today I would like to conclude with this statement that use GPS and GNSS and never get lost again, because it will always help you in finding your location better than before. Thank you.